Yeah, and I used to work for Erlang Solutions. So I left about 2 years ago. I've been at Datometry for about 2 years. So I'm going to talk about, so we had a project where we needed to support additional character set encodings, and that led us to a variety of discoveries about stuff that we had done wrong, complete misunderstandings of the terminology. And I thought this would probably be a really good talk because it's a very complicated topic. And reading the documentation from some of the vendors, you know, like I think the Microsoft documentation, I couldn't find it again, but I remember reading and it said, character set encoding is a very complicated very complicated topic. And then it went on to describe all sorts of things that were only slightly right. So basically what we're talking about is how do we avoid something that's apparently called moji baka, which is a term I didn't know about 2 days ago. But basically, it's the problem of when you have non-ASCII data, non-ASCII letters, you can often be in a case where they start to get kind of mangled. So the Japanese up there is the Japanese for moji baka, but if you don't handle it properly, you can end up with things that look like the next two lines. I mean, I don't know if anyone's had that experience dealing with multiple character sets, right? So the way I got there was like this. So I did this all in Erlang. I started with the moji baka, and we can see that that Erlang string is represented as these giant numbers, right? Each of the characters is one of those numbers. And then I tried to, okay, so what happens if we take that list of characters, encode it in UTF-8, then print it out as a string? Well, it all gets sort of mangled, right? And if you then say, well, a very common problem is actually double encoding data. So what happens if you do that again? Well, it just continues to get worse. And these letters, these A's with a little accents over, a different kind of accents over them, are a pretty good indication that there's some sort of encoding problem. So backing up, it's like, why is this so hard? And the reason that it's hard is that there's a lot of complicated terminology that overlaps and that's often used incorrectly. So it's very hard to understand what people are really talking about when they say character sets or encoding or, you know, what is Latin 1 versus UTF-8 and Unicode? Like, what do these terms really mean and how do they relate to one another? So we're going to talk about that. Then we're going to talk about how Erlang represents these things. As strings that we just saw, or as binaries that we also looked at, and why that's important to understand what's happening when you're using these things. And it becomes particularly important to get it right when you are trying to share data between applications. So I'll talk briefly about what our product does and why this became such a problem for us. That was very hard for us to understand. I want to start by going backwards a little bit in history, put all of this in a little bit of historical context, because I think it helps illustrate where the problems came from. So since we started using electricity, we've wanted ways of representing characters as bits, right, as ones and zeros. So you know, there's the telegraph, right, which is essentially a binary system. There's punch cards and there's paper tape, right? And the holes all represent the holes or not holes all represent the ones and zeros, right? By 1963, a standard emerged for how to represent character data, and that's called ASCII, right? To put that into some historical perspective, that was also the year that Doctor Who premiered and the year that the first Beatles album was published. Right, 1963. So that's how long ASCII's been around. The thing that's interesting about ASCII is it's a 7-bit system, right? So you don't use the 8th bit, so all the characters are 0 to 127. Which was fine for English, but wasn't so fine if you were not speaking English. If you were speaking some other, say, European language, where you might have letters with these accents on them. So here's an example of the problem that emerged with programmers using ASCII. So the different countries had their own separate 7-bit standards, okay? And so in ASCII, if you're a programmer, in the US or in the English-speaking world, and you wanted to program, you might have something that looks like that first line, right, with the curly braces and the brackets, right? That's a little bit of C code, almost C code. Then well, I guess it is C code, but in some national standards for character sets, 7-bit standards, those curly braces and brackets were reused for letters, right? So if you were, I think this is an example I found on Wikipedia from Germany, right? If you were speaking German and you were using a German character set, you didn't have the curly braces, you didn't have the brackets, right? So, but there's the same bytecode, right? So the bytecode 123 represents an open curly brace in ASCII, but it also represents the A with the 2 dots over it in this other language. Okay. As a side note, this is the reason why ANSI introduced these things called trigraphs, so that you could actually have use sort of more common symbols that were common across all languages to do the programming. So this is a double question mark thing comes from. All right, so that makes sense so far? Yeah. So you can use the same bytecode to represent different symbols, okay, depending on which character set you decide that you're using. Okay. So this was partially addressed in 1987 by the ISO 8859 standard. And in the US, we often refer to it as Latin 1, right? So Latin 1 extended the character set, the bytecode set, from 7 bits to 8 bits. So now we had a lot more, bytecodes that we could use to represent symbols. So Latin 1 incorporates all of the letters most commonly used in Western European languages. So the letters with all the different sort of accents on the top. But it's actually only one of 15 different standards. There's Latin 2 and Latin 3 and so forth, there's 8859 1, 2, 3 and so forth. And those other standards dealt with other European languages that didn't use the Latin alphabet. So like Greek or Cyrillic, right? But still, you were still reusing the same bytecodes because you only had 256 bytecodes, of which only about 190 can be used for actual symbols. Okay. And even this system had made no provision for what's called the CKJ languages, Chinese, Korean, or Japanese. There's no provision for that in this standard. Okay. So we kind of got a little bit better because now we had the different languages could all be represented in all the different, at least say in Latin 1, all the languages could be represented using a single standard rather than national standards for each of the different countries. Still, there was still this continuing problem that some of the, so this kind of this basically solved this problem with the different, with the letters, the accented letters replacing some of the programming symbols. So this was another example from Wikipedia where apparently Swedish programmers, when they were using ASCII and the national standard, kind of got used to these odd characters replacing some of the important letters. So in ASCII, in the ASCII bytecode, the O with the 2 dots over it the bytecode 124 in ASCII is the pipe symbol. Okay. And in the national standard for Sweden, that was the O with the 2 dots over it in the 7-bit system. In Latin 1, the O with the 2 dots over it is now character 246, right? So they've separated them, right? So now we have an 8-bit system that can represent all the Latin languages. So that's pretty nice. The problem was, at the time this was introduced, a lot of programs only dealt with ASCII as a 7-bit value, right? And they would use the 8th bit to do something else, like maybe it's the end of the word, right? So instead of having to put zeros at the end of the strings, you say, well, we'll just set that, the 8th bit, we'll save 1 byte, right? And today that doesn't seem to make that much difference. But when you only had, a few kilobytes of memory or hundreds of kilobytes of memory. It was kind of important to save those 1 bytes here and there. So a lot of programs all had to change to now become 8-bit clean. So there was a lot of programming work that happened. Okay, but still, like I said, no provision for the CKJ, right? So of course, people in Asia still wanted to be able to write things on computers, so they were developing their own standards. This is another something I stole from Wikipedia. There was a large collection of very confusing standards that were coming out of Japan and Korea and China for dealing with all the pictograms. And so this is a graph that's not that important to know the details of, but it's trying to show the relationships between the different standards. So not too long after Latin 1 came around, a group of people, I think it was in Berkeley, said, let's do something a little bit smarter, and introduced something called Unicode. So Unicode is a 24-bit system, right? So each character is represented by 24 bits, right? So now you've got over 1 million possible code points, right? So that's a lot better. And so the current Unicode standard has support for, or defines 140,000 different characters from 150 different languages, including historic scripts like Egyptian hieroglyphs. And it also has symbols, lots of symbols like mathematical symbols, and it has all the emojis, right? So those are all Unicode characters that are defined. Okay. All right, so now in Erlang, this is actually pretty easy to deal with, right? Because in Erlang, we usually represent a string as a list of integers, right? So now instead of the integers only being from 0 to 255, they are 0 to 1 million something, right? And each element of the list can still represent one character. So here are some examples of the word restaurant translated into different languages, assuming that the online translator I picked did the right thing. So we have restaurant, which is all in ASCII, right? So all the numbers are less than 127 or 128. We have Pectopod. When I went to the Soviet Union, we joked that it was Pectopod, but it's restaurant in Cyrillic. And you can see that the different character codes, the Unicode code points for the different letters in the Cyrillic, right? So now we've got this much larger space of numbers that we can work from. The next and so forth, right? And one thing that is interesting about this is that the European characters tend to be in the smaller number range, okay? And then as you get to the larger number ranges, they start to be more of the Chinese and Japanese characters, and then the very large number, the historic scripts and the emoticons tend to be at the very high end of the range, right? So they tend to be the biggest numbers, right? So there are some optimizations that some vendors make to say, well, so the optimization then that you can make is that the more in some, if you have a Western-centric thinking, the more commonly used characters tend to be at the smaller end, so we can use less, maybe we can compact it using that assumption. Okay. All right, so far so good? Okay. So now like I said, so in Erlang, this is pretty easy, right? But when you want to talk to something outside of Erlang, you need to be able to take these lists of characters and serialize them into a byte stream, right? Because that's what everybody else sees. And like I said, using 3 bytes per character, maybe not so good. People also complain about Erlang using 32 bytes per character, I think, because it's a list, and then there's the pointer, the reference, anyway. So maybe we want to be a little more memory efficient. So there are different schemes that have been used, that were developed, to take that Unicode bytes, the Unicode code points, and turn them into a byte stream. The easiest one to think about is UTF-32, which basically means you use a 32-bit value to represent each character, right? So since Unicode is only 24 bits, you can pretty easily map, how the characters are showing up in the byte stream. You could also do UTF-16, where you use either 2 or 4 bytes. So you can, if the character will fit in 2 bytes, then you do that. and then there's a tagging mechanism in the bits that's used to say, well, it actually needs 4 bytes, so we add a second 2-byte value and then mask them together in order to get the 24-bit value that's the Unicode. Right? So you can compact a little bit because, like I said, most of the most commonly used characters, if you're Western-centric, are in the lower range. So most of them will probably be in the 16-bit, the 2-byte per character. But the encoding that's most commonly used is UTF-8, and in UTF-8, there's either 1, 2, 3, or 4 bytes per character, depending on where you are in the code point range, right? So most of the commonly used characters, if you speak English, are going to be ASCII characters, so those will fit in 1 byte, right? And if you're using, say, Western European values, you're going to end up, because those are Latin 1 values, they'll generally end up in the 1 to 2 byte range, right? So you save memory, you save space. So here's that example again, using the Swedish word for sandwich, is that right? Yeah, sandwiches, yes, in the different encodings. So the first line is showing what the Unicode code points are for all of those characters. And then the second, third, the UTF-32, 16, and 8 lines are showing what how those characters would be serialized into bytes, right? So for example, the O with the 2 dots over it in UTF-8 requires 2 bytes. A 195, which is sort of tagging that it's a 2-byte value, and then 182, which is basically identifying that it's that character, right? Notice that in Latin 1 encoding, each of those characters only takes 1 byte. Right? So this 1-byte character, 246, which is the O with the 2 dots, needs 2 bytes in UTF-8. Okay. Good so far? Okay. 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 All right. Well, let me just, there's a few more slides to go through. Okay. So I thought we had more time. In Erlang, there's a couple of quick things that you need to do if you want to start using Unicode characters. The first is that tilde s does not allow non-ASCII characters, so you say tilde ts. The second is that the RE module you have to tell it that you want to use Unicode, so you add the Unicode option. And the last thing is when you start Erlang, you can tell it that you want it to use a different heuristic for printing strings. So instead of only printing lists of characters or binaries that are ASCII, that it should try to print anything that looks like it might possibly be Unicode. Okay. And then there's a bunch of functions that are used to do the conversion from character lists or do the encoding work in Erlang, which we'll just skip over quickly. One is the characters to list, and the other is, come on, go to the next slide. There it is. Characters to binary. So that allows you to encode from one character set encoding to another. So those are sort of the building blocks within Erlang. So just quickly, what our product does is we act as a gateway between databases. So we will ingest SQL that's in one dialect and translate it and write it out, execute it against a database that understands a different kind of SQL, and then translate the results back. So the challenge for us was that on the client side, the client could implement a variety of different kinds of character encodings. It could be Latin 1, UTF-8, UTF-16. And so we had to be able to respect that. And then also, yeah, I thought we had more time. OK, so we had to be able to respect that. And then also make sure that we weren't mangling the data as it passed through our system. So what did we have to change? So we had to remember what the client's preferred encoding was. We had to make sure that the backend server, so the part that says Amazon, Microsoft, Google, that we were talking to it in the character encoding that we expected that we were, because that's like it's a connection property, right? So it's mostly through ODBC, so it's a property on the ODBC server, ODBC driver. We had to change all the format strings, which was, thankfully, they were all easy to find because tilde-s is pretty unique to that. We had to change our calls to the regular expression module, and then things got a little bit harder. So there was a lot of places where we would use byte size, so we would have a string as a binary. We would use byte size to see how long the string was. Well, that only works if it's 1 byte per character, which is no longer true, right? So we had to find all of those, and those were not easy to all find, and change those to string length, which does the right thing. And similarly, for a character list, we decided that we should also start using string length instead of length. Oh, actually, no, that wasn't what. It was for IO list. For IO list, we needed to make sure that we were kind of doing the lengths properly. So that's fine. And then the last thing was that, of course, if you have a list of, you have a string that's a list and you want to convert it to a binary or a binary to list, we usually, in our code, will use list to binary or binary to list, right? But again, that's not right anymore, right? So if you have a list of Unicode code points, they aren't bytes, necessarily bytes. So you have to use a different kind of encoding because list to binary will throw a runtime error if one of the elements is larger than 256 or 255, right? Because it no longer fits in a byte. So we had to find all of those, change those to the appropriate calls to Unicode characters to binary and characters to list. To try to keep things a little bit more sane, we decided to standardize on how we would represent character data. Now, unfortunately, our code is pretty messy in sometimes storing strings as lists and sometimes storing them as, or carrying them through as lists or carrying them through as binaries. There's no clear layering of that, which is itself a problem, leads to a lot of coding runtime errors. But we decided, at least for this portion of it, what we would do is say when we read the data off the network and we're decoding it, it will be either strings of Unicode code points or UTF-8 binaries, right? So once it comes in, we know we're inside our code, it's a UTF-8 binary, which is the Erlang VM default for most of these things. And then we would only translate it to whatever was needed on the backend side when we got right to the network layer. Because otherwise, you might have these values floating through, and you don't know what the encoding is, and it can be very confusing. The other thing that we did was we made sure that we used test data that we could actually read, right? Because we could use test data that's Farsi or these funny Japanese characters or Chinese characters, but we can't really read them, or most of us can't. And so we can't actually know if it's right? Because you can't see visually that it's the right thing as quickly as if it were just European letters. So that was the other thing that we did. The problems that we ran into, the coding part wasn't too bad. The problem was actually figuring out what to do and how to understand what we were doing. And that was because the terminology was so crappy. The vendors that we work with, so primarily on the input side, we were translating Teradata. Their terminology was slightly broken. They referred to things as ASCII when they really meant Latin 1. They would talk about Unicode, but what they really meant was 16-bit characters. And Microsoft also had this sort of confused terminology about what they meant by Unicode. And making matters worse is that Microsoft also supports, actually both of these vendors support all these, remember that big chart of all the Japanese standards? They support all of those, right? So they also have all this confused terminology around that. So I think understanding the terminology can be very helpful. So that the distinction between what a character set is, which is sort of the encoding of the symbol to a number, versus the encoding, like UTF-8, how do you represent it as bytes, right? Those distinctions are important. And a lot of people, even within our engineering organization, would talk about UTF-8 as if it was a character set. And it's like, no, that's wrong. It's not a character set. It's an encoding of a character set, right? So just keep it simple. All right. Now, there's a bunch of stuff that can go wrong. So the biggest problem is that when you use the system, it can look like it's working correctly, but it's doing something completely wrong. And the common problem that we were seeing is that we were double encoding and then double decoding the data, because it's all the encoding is because the encoding outputs a list of bytes, a list of character points, right? That can then just be encoded again. So if you take a Latin 1 string encoded as UTF-8, think that it's a Latin 1 string encoded as UTF-8 again, and then reverse it twice, you get the right answer, right? But if in the middle you're storing it, you're persisting it, you're putting it in a file, what you have in the file is completely wrong, right? And that's the kind of thing that was happening to us. It's like, well, I inserted the data, I select it back out, looks fine. But then if you actually looked at the back-end database, it's like, no, that's not right, right? The data's all mangled. So that was also a challenge. Usually when someone will talk about it being a Latin 1 system, or Latin 1 compatible, what they're really telling you is that it's 8-bit clean. So here the problem is that you could take your you can take your Latin 1 data, encoded characters, encode them as UTF-8, so now you still have a bunch of bytes. But those bunch of bytes, it's just a bunch of bytes, right? So then you can say, okay, then I can write them into the database and tell the database it's Latin 1 data, right? So the database is fine with that because it's, oh, what's 8-bit clean? It's just a bunch of bytes, so I'll store them, right? And then you read them back out. You read them back out. You read them back out as Latin 1. Well, it's 8-bit clean, so no re-encoding happens. Then you decode it because you think it's UTF-8. You decode it back into Latin 1, and now you have the right answer. But the data on the database, in the database, is UTF-8 bytes, right? It's the string encoded as UTF-8, but the database thinks it's Latin 1. So if you were to ask that database, independently of our system, to look at that data, it's not going to be right, right? The lengths will be wrong. You wouldn't be able to select it properly and other things. So, and there's also a very common misconception we discovered that Latin 1 is not compatible with UTF-8, right? In other words, if you have a string that is a sequence of Latin 1 encoded characters, it's not going to look the same as those same symbols encoded as UTF-8, because the Latin 1 characters in the upper 128 need 2 bytes in UTF-8 to be represented, right? So what is true is that ASCII, 7-bit ASCII, is compatible with UTF-8, right? Those are exactly the same. And they're also compatible with Latin 1, right? But it's when you get to the upper range that things are not the same. So the other challenge is that if we look at this graph again, this chart again, encoding happens at all sorts of different layers. So you have some database client like, I don't know, SQL Workbench or something. Well, when it reads data in, it's using some encoding to show you the characters on the screen, right? So you have to figure out what that is. The ODBC driver that it is using may be encoding the data when it talks to us, right? And then on the back-end side for us, the ODBC server or ODBC driver that we are using to talk to the target database, whether it's Azure or BigQuery or Redshift, right? It could also be doing its own encoding of some sort, right? Because it's like, well, what kind of characters, what encoding is it expecting when you call it? What is it then telling the database that you've given it? And then even inside the database, sometimes that we found that it was, depending on how the driver was configured, it was also making decisions about how it should encode the data before it wrote it to the disk, right? And so it was very easy to have a combination of these things that looked like it was working, but in fact wasn't, because there were compensating errors along the way. And really the only way that we found to, the only way we found to really understand this was we had to look at the bytes, right? We had to say, okay, at this layer, what are the actual bytes that we are sending, right? And say, oh, that looks like it's UTF-8 encoded. It's like, okay, that's what we were expecting. And then just keep kind of going down the stack that way. Okay, so getting to the end here. Key takeaways, right? So a character set is some numeric value that's associated with a symbol, right? So that's what ASCII and Latin 1 and Unicode are doing. They're mapping a number to a symbol. When we talk about encoding, what we're talking about is how do we take those numeric values and turn them into a byte stream, right? So UTF-8 is an example of an encoding. So UTF-8 is an encoding of Unicode. And this only became important when a character was no longer fit. A character code, a numeric code, no longer fit in 1 byte. So we break the 1 character, 1 byte assumption. Right? That's when we start to need these encodings. Okay. Unicode is sort of the universal character set, right? It tries to capture every possible symbol, right? They're working on a standard for Klingon, right? So it's like everything, right? It's everything. Okay. And like I said, ASCII is compatible with UTF-8 and Latin 1, but Latin 1 is not compatible with UTF-8. The bytes are different. So encoding and decoding can happen in many parts, many layers of the system. So it can be sometimes important just to look layer by layer. What are the bytes? What's happening? And you have to be careful that the tool that you're using isn't tricking you, right? So we had cases, we wrote it, at a particular layer, we wrote it to a file, and the engineer was looking at it in VI. Well, VI was saying, oh, well, that's a UTF-8 character, so I'm just going to show you one. That's a UTF-8 symbol. It's a UTF-8 encoded file, and those 2 bytes are 1 symbol. So I'm just going to put 1 symbol on the screen. And the engineer's like, oh, well, okay, it's got the right length, it's got the right thing. And it's like, no, because we were expecting Latin 1 there. So we had to look at what are the actual byte counts, what are the actual bytes. And sometimes the editors try to be helpful, but they get in the way of actually seeing the data. So you have to use like OD or hex dump or something like that to actually see the bytes. And we've also run into issues when you do cut and paste. I mean, probably everyone's had this problem. Like someone sends you a snippet of code in Slack, and you cut it, and then you paste it, and it won't compile because Slack has changed the quotes, right? Same thing happens here. That it'll say, oh, well, that's a UTF-8 character, so I'll just I'll translate it for you because the standard is to pass this information around as UTF-8 anyway. And then finally, again, this double encoding and double decoding, everything looks okay, but at the equal sign, the data is not what you want, right? Okay. All right. So that's it. Thank you. And just a brief history about Datometry, my employer. We were founded 7 years ago. We just announced our Series B, completion of our Series B, and we're hiring. So if anyone's interested, just let me know. Thank you.
Thanks, Mark. Do we have any questions from the audience? Anyone?
So Elixir makes some very opinionated choices on characterless versus binary. So I'm wondering if you're familiar with that and the trade-offs that they made there.
I'm not super familiar with it. I do remember that there's a greater emphasis on binaries instead of characterless. I think that there are advantages to both. So one advantage of the way that Erlang does it is that when you do string manipulation, the data generally isn't copied, right? So if you cleave the list and put something in the middle, or you want to append to the beginning or end, right? There's no copying happening. Unlike, say, like a binary, where if you want to append to the end of the binary, if the buffer space that it's in is too small, it needs to actually copy the whole thing. So it becomes more like other programming languages, right? So on the other hand, binaries are a lot more compact. So if you had a table of values which are relatively static, maybe that's better to put in a binary, right? So you're not using up as much space. So I think it kind of goes both ways. For us, we do turn everything into characters, characterless, which is probably a mistake because most of the data is not manipulated. So for example, if you're selecting processing a select statement from a SQL select statement, the fragments of that which are the table names and the column names and all that doesn't change, right? So that would probably be better if we just kept them as binaries. So it'd be a lot more compact. Because we do end up with these giant data structures. So the way the product worked is that we use leaks and YEK. So we have like a 15,000 line YEK file that parses the SQL. And it generates an AST. It generates a tree, which we call a SQL op tree. And the queries that we are parsing can be quite large. They could be on the order of hundreds of kilobytes for one SQL query. And so that turns into a fairly large data structure. And sometimes these data structures could be this one tuple, which is the root of the tree in the tree. It can be hundreds of megabytes or even gigabytes. Yeah. Yes, in the back.
Thanks for the talk. Did you guys actually do any sort of useful tools that might sort of just generate fingerprints on files? I mean, you should be able to, just run something and look at the bit density to be able to figure out that file's got UTF-8 and whatever it is, and it's probably mostly 7-bit ASCII, but
yeah.
This one's got UTF-8, but it's actually mostly 8-bit. You could be able to just do some large-scale compute processing to figure this out.
Yeah, so the question was, did we do any tooling around using heuristics, I guess, to figure out if the input data is UTF-8 encoded or Latin 1 encoded? No, we didn't. But one thing is that it's possible to do that because of the way UTF-8 and the way Latin 1 and UTF-8 are designed as bit patterns. That if you now what is it? A sequence of Latin 1 characters will appear to be an invalid UTF-8 encoding. So UTF-8 was designed so that if it was a sequence of Latin 1 characters that happened to start with one of the markers, that if the following character had the byte has bit has another mask on it, and that mask will generally not match some of the other Latin 1 characters. So it is possible to use that as a heuristic to say, okay, so if I try to decode this as UTF-8 and it's invalid, it's probably Latin 1. And the Wikipedia page that talks about this says that there are sort of these cases where if it's like a sequence of an unusual sequence of punctuation, maybe it'll trick it. But no, we haven't done that. We have looked at the incoming queries because we get as part of our sales process, we get the query logs from the customers. And we do know that we've never seen non-ASCII queries, although apparently there was one that just showed up. But so that hasn't been a problem. The problem has mostly been in the data, and it's a little bit harder to do analysis on the data because we don't generally get the data from the customers until we're doing a trial. All right, any more questions? All right, well, thank you.